Okay, so you have had some time to try to solve this. This is exactly one step in the original GKP paper, but they don't compute explicitly this. So this is the exercise today. So, is there a particular step? Have you gotten the solution? Or no? Okay, so we will go in a detailed way. So the Wigner function of the code words of a QNIT encoded in GKP is given by this expression, where now the wave functions are the wave function associated with the code word J, the state J. If we deal with a qubit, then n would be equal to 2, and then we will have the state 0 and the state 1. Just that. This is generalized for a QNIT as it appears on the original paper. This encoding is used for protecting a discrete system against noise. So we encode this discrete system in continuous variables in this particular way, with this train of deltas. And now the Wigner function, we are going to use that definition. It will be something like this. I substitute already the wave functions. So far, are we happy with this definition? So I have substituted this wave function given by this, and the other, the only thing that I have changed is that I need to use other index, not S. This is a dummy index, so I use T. This is so far the only thing that I have done. Now I'm going to integrate. You know that the integral of a delta, what the integral of a delta is, so I integrate that. And I will have this. I will explain what thing I'm using now. So I integrate over x. And I integrate the second one. So this is going to be IP, and then in x, I'm going to provide this. And then in the other delta, I need also to write. Here, you see the factor 2. It's not very important. In the original paper, they compute proportionately. The only thing that I'm using is this identity. So here I have this instead of x. And this is what I am using. It's just that. Okay. Good. Have you followed? If you don't follow, just stop me. So I'm going to rewrite it a bit more compact now. Still, I don't have the solution that I want, or the one that appears in the GKP paper, so I'm going to rearrange the things. So now here I'm going to change the variables to this. So I take and say, oh, t plus s is going to be a new variable, t prime. And then t is going to be t prime minus s. It's just the same thing. And then, since I don't want to write all the primes, I'm going to call it the t prime, the new t. And this will be the new t minus s. And I'm going to change it here. So what I will have in the end is like, this is going to be and here I notice, I want, in the final expression in the paper, they have not exponentials, but two deltas. So you can see that the Wigner function is given by different deltas in phase space for different positions. So I'm going to do things to try to convert this exponential into a delta. This is the thing that I'm trying to do now. And then the first step that I'm doing here is to realize, like, okay, this is only different from 0 in certain points of Q. So I'm going to change that Q here, because anyway it's the same. So this gives me like this. I change the Q by that value. You realize that this is the same, because otherwise this exponential will not have support in other values of Q. And then I rearrange a bit more for using an identity that transforms the exponentials into deltas. This is just for being able to use this identity. This is a trick that we need to apply to get the expression that appears on the paper and get rid of these exponentials there. I'm going to erase the NOC. Is the step not clear? will send you all the, I will upload all the computations in detail.
Is it a big pi there in the denominator?
Yes, there's a pi. It's just I am rewriting this exponential in some way that I find convenient.
Or okay, it's a small pi. It's a, like, I mean, it's the normal semicircumference
Yeah, I
of
mean,
a circle.
Yes,
I just thought it was
yes,
a big
yes.
pi. I was like, what's the difference between the little and the big?
Ah,
Okay,
no, no.
cool.
No, it's the same pi. I'm using that identity that I wrote. So now I have something that I want, as it appears more or less in the paper. We still don't have the final expression, which doesn't have this exponential, but it's something closer. So the first time I tried to compute this, I was stuck here. I was thinking, how can I get other train of deltas? The trick is this identity. So in the paper they say, the Wigner function is what we are going to get. But when I tried to compute, I was stuck a bit here. Not too long, until I discovered that, yes, that this is the identity that I can apply. This is the, let's say, the trick that we have to use in this kind of computations. And then here, still we are not there, but we can see, apply a similar thing that we did before, and we see that this function is different from 0 only for these values of p. So we can substitute it there. So we see that we substitute the value of p, and it's we are now close to the solution, which is the following. Which is the equation 28 in GKP paper. Not exactly, they have a proportion. Actually, I might have committed some mistake with the prefactors here. But, so you see now what I have done. I substitute the value of p. Now here I take the fact that e to the minus I pi is -1. And then I have this, and then I have exactly the expression that I wanted. The big thing is the use of the formula there. This is the only thing that, and we need to know how to integrate a delta. But this is the thing. And then the question B, before doing the break maybe, is to see what percentage of this Wigner function is negative. You know that if we have a process in which the input, the manipulations and the measurements are characterized by a positive Wigner function, we can simulate that with classical computation efficiently. So the negativity of the Wigner function is important in providing advantage. Yeah. And then I wanted you to see what part of this Wigner function is negative. So if you think about the Wigner function as a quasi-probability distribution in phase space, where these are the quadratures, we see that this is a sum of deltas. So we will have some deltas positioned in different, for different j's. So for different states 0, 1, etc. We'll have different range of deltas. Like, I don't know what I'm drawing, but more or less like that. It's a lattice in all directions. If you ever see a Wigner function of a GKP, it's more or less like this. And some of these deltas will be negative, and some of them will be positive. It depends on this prefactor. So some of them will be negative. I don't know which ones. Now it depends for the state, but imagine something like that or whatever. At what fraction of the deltas would be negative? These states are not the physical ones, are the ideal ones, so they are not normalizable. So in principle, the Wigner function is the same all over the space. There are versions with it normalizable that Julia had in the notes, but we are dealing with these ideal ones now for seeing the thing. And we can see that S and T goes from -infinity to infinity. And then the only thing is like how many of these prefactors are negative. So we see that it can only be negative if both S and T are odd. If it is any other of the three other possible combinations, like even and even, even and odd and even, this will be even, so this will be positive. So the fraction of negative deltas is 1/4, corresponding to S and T both odd numbers. For any kind of code word.
Laura, how do you understand the negativity? Like, it's for me, it's like a lot of squeezing states.
Yeah, in the real case, it's like that. So
Is that because of the...
yeah, if you see it in 3D, I don't know how to. If you have a color map, some of these will be negative, less than 0, and some of them will be higher than 0, positive. So
is that because of some interference between those squeeze states so that they have this negativity? Or...
but the state is... Yeah, okay, but it's not only a squeeze state, it's much more complicated in the sense that if you have the real one and I go to the x axis, it will be several, like it's not only going to be a squeeze state, but several of them. Like ideally I would like a train of deltas like this, spaced by a certain amount. It depends on the code. But this is not real. So then I will have some kind of Gaussian envelope like this, with some kind of width here. And then of course I cannot extend it infinitely. So I will have another Gaussian envelope here. So actually the states would be like this. So it's not exactly. I don't know how to see the parallelization with a squeeze state completely. Maybe like you have several states like that. I don't know. This is, by the way, the wave function. This is the Wigner function, but it's yeah.
I was wondering if the negative parts is between those peaks. If that at the position.
The peaks are related with the peaks of the function. What's the function here? So for the code word here, you will find the peaks
Mm.
in the real space. But for example, you also have you can write that also in B. But if you see the delta of Q, the peaks are not exactly in the same position, are in half position.
So it's between the peaks.
Yeah, it seems like that.
Yeah, it's kind of between the peaks, but it's a different kind of I don't know. It's other quantity. It's a phase space representation. So it's related to this spacing for sure, but it's not exactly the same for Q. It's just other way. The phase space representation is other way of representing the information given in a quantum state. So yeah.
But actually, the positive peaks in the phase space, I think, correspond to the positive peaks in the wave function as well, actually.
But in the wave function, all of the peaks are
Oh,
positive.
sorry. Yeah, but the positive peaks in the phase space correspond to the peaks in the wave function.
Ah, okay.
Because
Maybe
you have-
it might depend also for the J. I don't know.
Because you alternate between positive and negative.
Ah, yeah, you mean because if you have here, yeah, could be. Yeah, but as I said, for me it's not so immediate. Like the Wigner function is a plot in the phase space.
But it's this quasi probability distribution function, right?
Yeah.
So it makes sense that when you have positive peaks, that's giving you a probability of the particle existing at that point, and the wave function is also telling you something about the probability of the particle existing at that point. The negative ones
But the
can't.
phase space representations, you need to be a bit careful because it's not as in classical physics in which you can associate. I can associate a probability of the particle being here with this position and this momentum. It's very different. What means to have a negative Wigner function? Then that's why I don't see the clear connection. It's other quantity.
I thought that if you have, I thought that the negative Wigner function is a position that's in phase space that is impossible, and a positive Wigner function is just corresponding to probability, or no?
No, I never interpreted it as a classical probability. For me, it's another way of representing the quantum state, but it's not. I don't think that you can do many parallelisms with the classical probability distribution.
I thought that was like the whole point.
What means to have a negative one?
Well, it's something that's impossible. It's just something that can't exist. Ingrid, in her defense, she said it's
Who
like.
said that?
She said it's like, what is the probability that what was it? She said there's a -30% probability that it will snow tomorrow.
It's reasonable to have the negativity in the Wigner function because of this uncertainty principle. Because you cannot just measure the P and Q in the same time, so you have a you need to
you can't,
integrate
it's
it.
unthinkable. Yeah.
If you integrate that error, then it's positive.
Yeah.
So
But then that gives you a probability, though, right?
yeah, but you need to integrate
Right.
all the.
But the Wigner function does correspond in some way to probability.
If you integrate.
If you integrate, yeah.
Yes.
Okay, then. Okay, maybe I was mistaken. Then I honestly I never think of it like with this interpretation. I always use it as a. Yeah, but of course you can get from the Wigner function is the only phase space quasi distribution from which you can get the probability of P and Q. So now that you say it, yeah. If you integrate on the other.
But it's also interesting that the negativity lies in the right in the middle of the peaks, and they're delta functions as well, right? So it's like you have Wigner negativity, but it's just like dotted right in between the peaks of GK peak rating?
Yeah, I mean, why it's used exactly in the middle? You mean like it's in?
Well, I mean, yeah, no, I don't know. I mean, I guess it's just the maths.
Yeah, I see it only as the maths.
Yeah,
Maybe
yeah.
I didn't do the extra step. For me, it makes sense that it's that symmetric because it's already symmetric in the wave function.
Yeah.
So it has some kind of symmetry for encoding the discrete system, finite system. And for me, it makes sense that, okay, I have some kind of translation symmetry there. I see here a lattice. Then regarding what about the peaks, then but honestly, I never thought about the negativity in that way of probability. Of course, if you consider the integral, then yeah.
But hang on, if you integrate, for example, at p
Wait,
equals 0.
1 second. Should we do the
Sure.
stop and then
Yeah.
have some 15 minutes?